Right, so welcome to my presentation, or I guess short video on this simulation of an epidemic that I created over this week. This is for a project, or I guess a little competition held by some high schoolers at Nagoya International School, and I thought it would be interesting to join and see what I could do. Anyways, let's get started. So, the first thing, all of this really started on the 8th of April. I don't know how I still remember this day. Well, it's not like it's been such a long time, but it's been about 2 weeks ago. Anyways, so on the morning of the 8th of April, in homeroom, we got this news that students at Nagoya International School were doing a programming competition. And they had a whole website. The design was amazing. I didn't know how they really made it. The logo for JHack, I actually really like how that looks. And so I decided to join the mailing list, just typing in my private email address and seeing how it would work out. At this point in time, I really didn't know if I would do it or not. The thing was set at April 26 to 29. I still had school. It was before Golden Week. I knew I was going to be busy, but I was like, this might be something interesting. But something you might have noticed is that, yeah, this thing was started on April 2nd, and I got the news in my homeroom on the 8th. So all this information was out. Everyone probably already saw what they were doing, and I was already 6 days late, and it's not like I'm a coding person that could catch up on this thing, so it's pretty worried about how I should go about this thing. But at the end of the day, you might have saw the first slide and might have been able to tell, but I didn't do anything for 2 full weeks. On the 8th, I heard about it. I was like, oh, that's neat. But till the 23rd, 24th, I was like, I have better things to do. I couldn't really get started on this coding project. And where I really stopped was what to title the code. Because I didn't want to just title it like covid.html or like index.html. At the end, I ended up using bear.html. This is something that my friend came up with, but I couldn't really tell if that was a good idea or not. Anyways, but after that, after I finished making the project, I decided to retitle it to chocolate.html, and I was eating chocolate at the time, and I thought it would be such a great idea just to title it something that has nothing to do with what the actual project is about. Anyways, so on the 24th, I think this was a Saturday, I decided to start coding and use HTML, CSS, and JavaScript. JavaScript was HTML and CSS I've actually tried to use before. I did button designing, so I don't know why I was doing that, but it was really interesting. I would make buttons, hover over them, and make it do something. But JavaScript was really, really new. So first thing I decided to do was see if I can make it say hello world, and it was pretty simple. The script's on the top right. This is actually, if you copy this onto an HTML file, you'll be able to use it. This is like this whole script thing, I guess. If you put it between the scripts, it acts as like a JavaScript file. So you can code it from there. Anyways, it was really interesting adding on to this new language, and I realized that it would be really nice to use this because CSS, as far as it goes, it's, I guess, like formatting, styling, it's in the name, and you can't really animate things, and if you wanted to draw or animate things, I had to learn to use JavaScript. It actually turned out better than I thought, so that was really nice. So the second part was planning. I got the JavaScript working. It was like everything was fine. I was able to type hello world. It connected with my HTML and CSS files, so I was like, okay, let's start using this. But I had to think about what to do. So first to plan the user interface, because this whole project, so what happened was we had to choose from one of several options on what kind of what do you call this, topics to go about doing the project. And I live in Osaka. The COVID cases were rising sharply, that I thought it would be a really good time to make a project on awareness. So if you see on the left-hand side, it says, as the pandemic has dragged on for many months, many people have become numb to the dangers of COVID-19, especially as countries have begun lifting lockdowns. Build a project that seeks to rectify this issue. So I decided to make a COVID or epidemic simulator, which would give the users the power to try different combinations on inputs and see how it affects the population, so that they could really feel how important it is to do certain things, like, I guess, washing your hands, wearing masks. And as said in the previous slide, the whole plan was really simple. I would plan out what I want to make, just decorate it onto my notebook, see how I want to shape it, actually code it, make the simulation working, and then I was done. But it turns out, no. Oh, I thought the coding would be easy. No, it wasn't. It was glitching everywhere. Particles were flying all over the place. Nothing was really working perfectly. And it took, I think, 2 whole days just to debug everything, make it seem like it was working. And then I feel like I could still find some errors here and there, but I didn't know what was causing it, so I couldn't really fix some parts. And then, yeah, I didn't really cry, but I was about to cry. It was really tiring because I had to finish it to actually make it work. But if I wanted to finish it, I had to add a new feature, which would always glitch the whole thing, crash it, and then redo the debugging. It was finding errors, fixing them, adding something, finding errors, fixing them, repeat. It was really tiring. But after that, after a feature started working, I was really happy because it felt like everything, all the work that I've done, seemed to have fixed everything itself, and that it was working. But on the other hand, it's coding. Sometimes I was just missing a parenthesis, sometimes I just had a typo. Everything was really interesting in that sense, but yeah. But it works now, and the coding is finished. It's uploaded on GitHub. So it's nice to see that it actually worked. But I did get to step 3, and I did finish my project. That's why I'm able to record this video right now. So that's something really nice. So this is the coding that I started from, 4 days ago to yesterday. I actually was debugging until today, so maybe I should change this to 29th. But anyways, it went on until yesterday night. I was actually talking to one of the admins that was in charge of this, asking how I could use the hub properly, and I really didn't get it to work until the end, but it was an interesting conversation that we had. It was barely anything to do with coding, rather more like, oh, hi, how are you doing? Yeah. So this is a slight peek into what happened. I needed to code the whole project, and to do that I required help from a lot of different places. But at the end of the day, this coding, my computer would just do random things. Everything. Stack Overflow helped me. There was errors, such inefficient coding, and errors after errors after errors, and Stack Overflow searches. Everything was so bad for so long, and then this comes up every once in a while. I'm using a text editor called Sublime Text, and like every 10 saves or 20 saves, this message pops up, and I could use the whole thing without purchasing it, but I would have to click on cancel every time. It was really hard sometimes when I was trying to get over an error, and this comes up, and I'm like, maybe I should stop coding and just get to sleep. But this was really funny when it came up because I'm on like the verge of, I guess, like stopping coding, and then this message shows up, and I'm like, oh yeah, maybe I should go back to coding. Yeah. So I guess this message really helped me. But other than that, I looked at Stack Overflow so many times in so many areas just to try to fix or like try to do something. It was really hard in that sense. So yeah, I might have had some troubles, not too many. But I did end up, as I said, with a finished project, and I can show you. Oh, no. It's a simulation. You don't need Wi-Fi. So this is what I ended up with. This is what the front page looks like. You have the settings on the right. Instructions are on the left. You can actually get this from the hub. Try it out for yourself. If you click on Start Simulation, yeah, that's the parameters. There's 1, 2, 3. There's 8 main parameters and 5 more little options that you can select. And these things would completely change how the simulation works in terms of how slow it would infect, or how laggy it is, or how much, yeah. So in my simulation, red dots represented infected patients, and if I would, I guess, increase the radius of infection to like the maximum, those red dots spread so quickly. It was really scary seeing how, like, imagining that it's a actual virus, thinking that it could spread that fast was worrying to some extent. And this is the simulation page. After you click on the start button, this is what shows up. This is a specific setting that I put it on, so not everyone would really see this exact screen, but this is about what you would see if you were to click on start and make the simulation start running. You can see the initial parameters on the right side right now. I don't recommend using this specific layout. It's just so that I could show all the buttons at the same time. But if you do this, I think the whole simulation would turn out to be a little bit slow. Yeah. Okay, so this is the part that I'm doing today. I was going over the simulation, testing out different methods, seeing how each one would act out. This was, I guess, the best part of the code because everything was complete. I would just play around with what I made. Right, so my code uses a SIR model. Every population, which is represented by a dot, is given either susceptible, infected, or recovered. Susceptible people are in blue. So, this one. Here you can see the blue dots everywhere. These are the people that are susceptible to the virus, that they can actually get the virus if they're too close to the red patients. And after the red patients wander around for a little bit, they become dark grayish colors, which represents that they've recovered. So each dot has those 3 states. They start off as susceptible, and then they might get infected and recover, or they might not get infected at all and be able to live until the end. So this is the model I decided to use, and this is a good model in the sense that it's really simple to use, but it's not completely the best in the sense that it is a simplified model. It's not an accurate representation of how complicated our society is, but in terms of how my power to code, this was, I guess, the best model that I could use. So to begin things off, I started by doing a control test. This is the initial default settings. If you just click on start, this is about what you should get. I mean, the initial, it varies time to time depending on how the population is laid out or where the first infected person spawns, but you would usually get less than, I guess, 100 people left at the end, and would continue for 30 to 50 days. You could see the dots spreading. It's not as fast as you would think or imagine, but if you change the settings, this really changes. And this is the whole point of why I made the simulation, but this is just a control test to show what it looks like if you just do nothing to the virus, I guess. So if you decrease the radius of infection, you could just change it on the settings. If you change this, which is, I guess, equivalent to the population wearing masks, you can minimize how far the virus can be transmitted by every person. So then if you do this, you can see that even after 40-45 days, not too many people are infected. In fact, the infection is really, really slow and actually slows down near, I guess, 50 days. So it really shows how significant it is to be able to wear masks, get safe so that the virus doesn't get transmitted. And this also brings up one thing, is that in this scenario, it's important for those who are infected to be wearing masks rather than those who want to be protected to be wearing masks, because the people that have the virus are the ones that are spreading it. So it's really important for them to be careful to be able to decrease the radius of infection, because even if the people that are susceptible are wearing masks, all they can do is, I guess, protect themselves from the incoming virus. But it would be better if the person with the virus could stop it with their mask and not make it fly far away. The second thing I tried out was decreasing the probability of infection. What happened was, this was actually a smaller effect in comparison to decreasing the radius of infection, but it did minimize the speed at which the people were infected and how many people survived until the end. I think more than 100 people usually survives in this setting. And one thing to note is that in this setting, I think the maximum active patients are usually about 140 to 150, but in the initial settings, it usually goes up to about 180 or 190. So it does show that you could reduce the speed of infection, and that's really important because I guess we live in a world with finite number of hospitals, so if the amount of active patients goes over a certain amount, we might not be able to take them into hospitals. This is actually happening right now in Japan. In my prefecture especially, we're not able to have even the patients that are about to die to be able to get to hospital beds. So decreasing the probability of infection to slow down how fast the people are infected is also really important. And this is, as it says, equivalent to the population staying sanitized, because if you're sanitized and get off the virus from your body, then even if you did encounter it, you might not get it if you're able to, I guess, put alcohol on your hands or like wash them off and stay sanitized. So that's something that's also really important. And so this is a brief summary. You can compare the graphs and see how each option changes how the infection turns out. A control is the initial settings, reducing the radius. If you look at the dark part, that's the amount of people that's been infected overall. So that shows that the control has much more people that got infected in comparison to reducing the radius of infection or the probability of infection. One reason that the radius might have had a much greater effect is that reducing the radius from 10 to 5 is really big considering how our simulation's laid out. There's only about 1,000 dots, and the average distance that each dot is away from each other is more than 5. So that might have been one reason that everyone was not getting close enough to each other to actually get infected, and that's really important in the sense that it also means that distance works. So if I'm near someone with a virus, but I make sure that I don't get too near them, then it means that I'll be safe safer because I'll have a lower risk of actually getting the virus transmitted at me. And on the other hand, this is a reverse version where I doubled the radius of infection and I doubled the probability of infection. In both cases, you can see how so little people survived until the end, and in terms of the doubling the radius, you can see how fast everyone got infected. By day 20, the majority of the population was already infected and was only declining. And you can see how, I guess, doubling the radius is pretty much like coughing in public without really covering your mouth, or doubling the probability is like not showering, I guess. You might be really busy and online staying home, but it's really important to stay sanitized to keep yourself really safe so that when you go outside, you don't have the dangers of getting the virus, or if you have the virus, that you don't give it to anyone else. So one of the keynotes for this section is that the speed of infection is affected mainly by the probability in which patients are infected. This, I guess, represents also the duration of interaction and how well you're sanitized. And it also is affected by how spread out the virus is. Moving on, this is another feature. This is one of the main features that you can use, is adding a central location. What happens is, every once in a while, one dot would travel to the center of the board and engage in, I guess, like shopping or interaction, amusements. It's essentially like a marketplace or a city or area that people visit. And what happens is, if you come from a distant area, you can see on the top right image, this is actually during the simulation. It started on the top right, one dot on the top right moved to the center market. An infected patient infected their virus when they were at the center, and when that person went back to where they originally were, the virus moved to the other side of the board and started another whole set of infections there. And this process dramatically increases in speed the more positive patients there are, because that means that everyone's going to the market, infecting everyone else, and those people are going everywhere else on the board. So it shows that if people go to the city or a supermarket or a market just in general, it's really dramatically speeds up the process of the infection and how hard it is to, I guess, contain it. Because if it's on one side, the people can tell where the virus is approximately at. But if someone goes to the market, meets someone else, and that person gets the virus and takes it back to where they came from, then it becomes extremely difficult to stop the virus from getting to everyone else. This is an additional feature that can be used. Instead of having a central location, the setting is to have multiple cities that people travel between. So you can see that the top left is where the infection first started. That part gets the most damage. Well, it seems to have the most damage initially. And what happens is, every once in a while, people move between the cities. So if an infected patient moves to another city, they start the virus there. But on the other hand, it also means that as long as no positive patients gets to one city block, then everyone in that population would be safe. So take the bottom right box in this city, for example, then everyone here will be safe as long as no positive patients enter. You can imagine this as, I guess, instead of cities, countries. Countries blocking airports or borders would allow them to stay safe as long as there's no virus in the country. But if they act too late and a virus enters their country, then it would spread out and it would be really difficult to contain because it's already spreading inside the location. And something that was interesting was that this effectively is the same thing as the control. It's just that there's less people moving between the borders. So although it takes a little bit more time, there's about the same amount of people that survive as the control, if not more, on the assumption that one city stayed safe until the end. And this setting is having a central city. This is one of the option features implemented. What happens is the population is centered around the center, and the edge cities or areas have less dots, so those places, I guess, are safer to roam. You can see how this is true on the images on the right. The central city has so many infections that it spreads out. Even if the radius is the same, the population density is greater near the center, so you can see that the people have to interact and then they spread the virus at a faster rate. But on the other hand, if you're on the edge, the radius would probably be smaller than how far away you are with another person. So even at the end, many people survive if you're near the outskirts of the city. And it's really important because in this mode, people still do move between the cities. This means that if there's an infected person in the central city, then they could go to the edge. But even then, you can see how much more people are alive or haven't gotten the virus even at the end when you are in a more rural city. This also shows how staying away from each other or socially distancing is one of the most effective ways to get away from the virus and stay safe. So this is the second brief summary. In comparison with the control, both a central location and populated cities dramatically have a much higher peak of infection, and in that sense, it's really harder for hospitals to be able to go around and help everyone at the same time if they don't have such capacity in how many people they're able to take in at one time. And one thing to note is that having a central location is really dangerous. You can see how little people are susceptible at the end. Having a central location really forces everyone to go there, and when you go there, even if you didn't go there, someone could get the infection and come back to where you are and get the virus from there. So you hear a lot of stories about how maybe your friends or parents went to the city, came back with the virus, and you also got infected even though you were making sure not to go to the city. So this is something really dangerous and we should focus on. We even in real life we say that if you don't have to go out, just don't go out. And this really shows how that's true and how dangerous it is to go out when you don't need to, and going out too often could infect so many people. And you might think that is a certain population still alive at the end in this scenario, but this is more like that there wasn't enough infected people at the end because everyone just recovered or died, that they couldn't infect anyone anymore. So this is a really bad scenario because I guess like less than 20 or 30 people are alive or susceptible at the end. So this is the second keynote, and the speed of infection is affected by the frequency of interaction. So making sure not to visit cities is a really good idea. Visiting heavily populated areas, if the infection radius is constant, then if you're at an area with a higher population density, then you're more likely to get the virus. Rural areas are naturally distanced, so are safer in comparison to urban cities, but that also means that it's not always completely safe. You saw before that there were still people that were infected. And infection on the central city, it leads to a drastic increase in infection, which can affect healthcare. Just to show you this, here on this slide, on the bottom right side, you see a dramatic sharp increase at about day 9 to 10. This is when the first infection went to the central city. And from here, there's a drastic increase in the active infections. And because it's the central city, people move from and to the central city. So that causes the virus to go everywhere else, which is dangerous. And as much as the rural people are safe, that doesn't mean that they're like completely safe. They just have lower risk. So it's still important to be really, really careful. The next feature that was implemented is isolating positive patients. You see this often, is that if there is a positive patient, we take them to the hospital, make sure that they don't interact with other people so that the virus doesn't spread further. So in this setting, you can create this quarantine zone that you could consider this like a hospital, that every time there's a positive patient, they're identified and they're taken to the quarantine zone where they are kept until they recover. And something that was interesting is that if you're able to quarantine every infected patient early on, then the total infections is extremely small, but this requires you to have extremely fast reaction time and extremely fast quarantining. You need to be able to identify them quickly, test them to make sure that everyone's safe, and then take them all in, which in a sense is unrealistic. So a more realistic speed would go something like this, where patients would be isolated at about the same speed as they were infected, are being infected early on. And so what you can note here is that even though you're quarantining people, what happens is it does slow down the spread quite a lot. But if the active patients go over a certain level, then the speed at which the patients are being isolated can't catch up. So you're going to get more patients and more patients that you need to be able to like put in your hospitals, but you're not going to be able to because there's more patients being infected than you can handle. So this is what's happening near, I guess, day 25 to 30 and day 40 to 45, where you are quarantining, but I guess it could be like a cluster. Maybe one of these particles moved to a place with more people, and it could have caused a massive infection. And then what happens is, from like, I guess, day 5 to 20, you're isolating patients at the speed at which people are being infected, but at day 25 you can't do that, and there's more people infected now, so more people keep getting infected, and you can't stop this process unless you increase your speed of isolating patients, which is pretty hard to do because increasing the speed of isolating them means that you need more hospitals available and open to keep them and keep them healthy and make them recover. So realistically, what isolating parents at is good as long as you can do it at an early stage, but if it gets too late, the speed would probably not be able to catch up to how fast everyone else is being infected, and it would only be a matter of time until the hospitals cannot take any more patients to help recover. So, but in a more, I guess, realistic scenario, patients are asymptomatic. This means that they don't show up to have any symptoms, so they can't be identified as a positive patient. You could also think of this as people that don't take the test to see if they have the virus or not. And what happens is these patients are never quarantined, these yellow dot people. So what happens is they just wander around until they recover and keep infecting more and more people, which leads to a faster infection rate. So more people get the virus, which is obviously not a good thing. And this is what happens at 20%. You can see on the bottom right. It's actually decently okay. Not that it's good, but it's definitely worse than this one before, where the infection rate is spread out. But in this one, it is a little bit more spread out because you are still isolating patients. But again, because there is a certain percentage of asymptomatic patients, people are still getting infected, and you can't really stop this from happening. So it really shows that isolating patients is a option to take, but it's really, really hard to do realistically, considering how many people might be asymptomatic spreading the virus. Even if you think you contained it and everyone else tested negative, there might still be a positive patient that you can't identify that keeps spreading the virus, and then you have to start the process all over again, and then it's really, really difficult to contain. If you increase the asymptomatic probability to 80%, you can see so many yellow dots now, then it looks more like the control, because essentially if 100% of the patients are asymptomatic, then the quarantine zone really does nothing. So I guess isolating patients to the control is pretty much like a range at which the percentage of asymptomatic patients determines, and it's really, really difficult to quarantine the patients and keep the population safe when there's so many asymptomatic patients, because the quarantine zone really can't do too much work because it barely identifies the positive people, and by the time that they've taken those 20% of the positive patients, the other 80% has already infected more people. So the third keynote is that the speed of infection is affected when isolating by the speed at which it is isolated, in the sense that how fast the people are being isolated. So if you isolate people really quickly and outtake the speed of infection, then you'll be able to go back to 0 active patients. And the percentage of the asymptomatic patients determines how effective the isolation is, because if 100%, as I said, is asymptomatic, then isolating, you wouldn't be able to find anyone that's positive, but the virus would keep spreading. And quarantine causes the peak of infection to decrease, but cannot stop infection if it spreads rapidly. This is something that I went over multiple times. But one good thing about isolation is that it does slow down the spread. So it does slow down and spread out the spread. So if there's a research center trying to make a vaccine, then this could be an option that would slow down and give more time for them to prepare their vaccine while keeping as many people susceptible as possible. And the fourth section is social distancing. You can see these dots that I circled. It's really hard to see when they're static images, but this is an option where they're socially distanced, and they're distanced enough that by the time they all encounter someone else, they're already recovered, so the infection can be kept at a certain area instead of making it spread out to the whole place. So if a government, decides to say, okay, we need to socially distance after they get about 100 patients infected, then what happens is there would be a major area where the virus would have taken over, but there would also be another area which the virus would have never reached because they're socially distanced and they're making sure that they don't go near each other, which also means that they wouldn't move too much from one location to another. So the virus would be kept in one place rather than spreading all over. And this is something that's really, really significant to go over, is in real life, although we socially distance, or I guess this could be taken as lockdown, socially distancing is really effective in the sense that it does slow down the spread and in fact reduces the number of active patients, but it's also something that humans can't do for such a long time, and after a certain length of time, people would just quit socially distancing and go back to their original lives, or the lockdown could be lifted and we might think, oh, it's okay, we could go back to what we were doing before. And then what happens is the patient's number starts growing back again, and really what it could do is that it would have slowed down the infection a little bit, but there would be another second wave. You might put another social distancing there or lockdown there, and then if you lift it again, there could be a third wave. This is something that's really happening in, I guess, Japan as well, where the government tries to say, okay, we're going to do this, and then the infected population goes down. But then by the time it goes down, they're like, oh, we can lift it, and then they lift it, but then the number of people infected starts rising again, because it's not like they've contained everyone, it's that there's still a certain population that's actively infected, which then starts moving again and infects everyone else. So if you're going to be socially distanced, it's really important to constantly keep doing this, because if everyone's moving, you really can't stop the virus from getting to you. And something that's really significant, another thing that's really significant, close to what happens in real life, is socially distancing, but also with having a central location. This is one of the features that we went over a little bit ago. What happens is the spread slows down, but people are still getting infected here and there. So you need to keep socially distancing for quite some time. You can see before on this part that if you were to socially distance for, I guess, like 5 or 10 more days, then the infection would have been wiped out and they would have eradicated the virus. But here, although the social distancing is continuing and the virus is being kept at one location, because people are traveling to the central location and they're spreading the virus there, the virus moves on to different parts of the community or area, city, I guess. So the virus keeps getting to one place, spreading a little bit there. The virus moves again, spreads a little bit there, which really lengthens how the population is infected. Even though they're socially distancing and trying to stay safe for such a long period of time, they're still active patients. And what's really, really bad about this is that after all of this, I guess 45 days of socially distancing, if they lift the lockdown, or if they say you don't have to socially distance anymore, what happens is something like this will happen again, and everyone gets infected. So even if the majority of people are making sure to socially distance, if there's a tiny fraction of people that move and visit, I guess, central cities, which I know some people have to because they, I guess, need to buy their groceries or something. But if you do this, it really makes it difficult to contain or stop the virus from spreading, because you are going to be meeting or seeing or going near people that you don't know that might have the virus. You might have the virus that might spread it to them, and they're going to be going off to another place somewhere else in the city and spreading it there. So this is really, really dangerous, but it also is really, really similar to what's happening in real life, so that's important to note. So this is the fourth keynote section, that the speed of infection is affected when socially distancing by how early the people start to distance and whether they continue to distance. It's really important that the second part is really, really important in the sense that if they don't continually distance, then it almost ruins the first section of socially distancing, because you still have patients that are active, and those people are going to just act like the first patients and start the whole wave coming again. So that's important, really important to note, especially from what we can see in real life, and it's applied and shown as well in this simulation. And finally, visiting a central location while socially distancing causes the infection to continue for long periods of time, even if you continue to socially distance. So that's also something to take. And this is part 5, what we can take from the results. So something to note is that COVID is still around. This whole simulation is supposed to be an epidemic simulator, but COVID is something that we can really, the things that COVID is doing to our society is also reflected back in the simulation. And because COVID is still around us, this is something that's really, really important to still keep in mind, that if the virus isn't completely eradicated, there is always a chance that you will get it in the next wave. If people start lifting lockdowns, I guess, then you get another wave that you might get infected in. And what you can see is that even if you socially distance and stop it stop socially distancing, the second time, by the time you socially distance again, the virus is all over the place and it's not contained anymore. So although it might seem like, oh, we're just going over another wave, every time the wave comes, the virus is getting much closer to you. And I personally experienced this myself because one of my friends actually got the virus. Um, and this happened, I guess, pretty recently. And back when it was still on like the first or second wave, we were only hearing news that we got it in our prefecture, we maybe got it in our city, but now it's like we're getting it in our school, so we really see how the virus is coming closer to us. And so just to go over three main key points that the simulation shows that's really, I guess, applicable to real life is that lifting social distancing only makes the cases rise again. And so it's really important that if you're going to do one policy, that you stick to it and make sure that you can do this until the virus can be eradicated. And visiting the city, even when socially distancing, will lengthen the time taken to eradicate the virus significantly. As I mentioned before, this is because even if you're socially distancing, if you visit the city, you might infect it, city or market, you might infect it to someone else that's in the market, and they might take it back to somewhere else. And if there are more cases that are isolated, quarantine will not be able to slow down the spread of the virus enough. I mean, this is, I guess, something fairly obvious, but it's something that's also important to note because even if we keep testing and we try to slow down the spread, this means that if our rate at which we can isolate the patients is smaller or slower than how fast the virus is spreading, then the total active patients keeps increasing and we wouldn't be able to um, contain it, and this is why they would be considered an epidemic. So what can we do about this is that by making sure to stay safe by sanitizing, wearing masks, socially distancing is extremely important to keep yourself safe. You saw in the first part that reducing the radius of infection or probability significantly decreases the total number of patients that get or population that gets infected at the end. So you could be more safe by making sure to sanitize, wear masks, and to have this awareness that the virus is still there and that it's really dangerous. Another thing you can do is to visit central locations less. You've seen that visiting central locations has a significant effect on how long the virus lasts, how fast it affects you, and how even social distancing policies, which is probably one of the most effective in terms of this virus, would not stand a chance if people are still going to the city. And yeah, and the third thing is that to understand that you and the other people's actions can accumulate to make the second or next wave of the virus worse. You having to visit the city might cause another person to give the virus to you. You might take it back to where you are, spread it in your community. You might have the virus and spread it to other people's communities. That your actions and what other people's actions do, the I guess social awareness that we have has a large impact on the country or the world's whole lifestyle. So it's really important to understand that these small actions that we take by just simply sanitizing or just wearing masks has a large effect on the community if you think of it in terms of if everyone is able to follow this. And finally, well, one very, very important thing to do is that even if the virus has lasted for over a year and we think that it's getting better, we still need to understand the dangers that the virus has and how we can stay safe. It's pretty obvious. I don't think no one would want to get the virus if they can. So it's important that we make sure to stay safe and keep the risk low. Even if you try to stay safe, there is always going to be someone that gets infected, which happens. It's not something that you can stop, but what you can do is to make sure that we can contain the virus and to make sure that it doesn't spread farther. What happened with coronavirus is that the initial reaction by the Chinese government wasn't fast enough. So it spread all over the world, and we couldn't contain it in one location. So at the end, now it has become a global pandemic that every country is dealing with in their own ways. So in that sense, I'm not blaming China for any of this, but if that country was able to isolate the patients at a earlier stage, then maybe the virus wouldn't have spread as far into the world like what's happened right now. And I guess those are the main things to take away from what you can see in this simulation. So, this is a little bit going off topic, I guess. But for the users, I have created this project. The main point of this project is to raise awareness about the dangers of COVID, and the simulation isn't only there for me to use to explain the dangers, but it's also for the users to try out how each option might affect other people, how fast the people get affected, how many people get affected. So the simulation is open for anyone to use. It's made so that it should be pretty easy. You simply adjust the settings on the right side with the parameters on it, and you just start the simulation, see how it goes. So I decided to create 2 game modes on the simulation to make it more interactable and fun. And the first game mode is the one that I've been using for this presentation. You can toggle the settings in the beginning or during the simulation, unless it's like the initial population, which you can't really change midway. And you can, I guess, try out different combinations, see how it goes, see how it plays out. Maybe you might want to try increasing the infection radius to maximum, see what happens. It's really scary. Everything becomes red instantly, even if your probability of infection is really, really low. That's something that's also interesting. And the second game mode is high score. In real life, it's not like we have the perfect power to keep everyone equally socially distanced. Some people are still going to be moving. Human behavior is really, really hard to predict and to change. So this game mode is aimed at saving as many people as possible while also using minimal resources. What happens is governments have to go through this choice on keeping the people safe, but also at the same time maintaining the economy. Socially distancing for long periods of time leads to people not going out, which is really bad for the economy. But at the same time, if you try to make the economy better and make people move around, then more people get infected. So it's a hard job for the government to try to determine their policies to keep everyone safe, but at the same time also maintaining everything else. And so this game mode is set so that you can try out different settings, which they all have different weights that would change your multiplier. And your goal is to have a high multiplier, which usually is a hard setting like increased probability of infection, increased radius, while also trying to keep as many people alive. So a combination of, I guess, policies that you try out to see would be effective in containing the virus. So that's something that I hope anyone watching this could try to use and enjoy if they can. And finally, this is final things to say. I know this video is really, really long. I think I've been talking for over 15 minutes now. This project overall has been really fun for me. I've learned so many new things while doing this. I didn't know how COVID was really spreading in my location or what it was being affected by, but this simulation really made me understand how important it is to do certain things like staying sanitized, wearing masks, and at the same time it really gave me a new chance to look at the virus again and raise awareness about the dangers that it has. So I think, as if anyone's watching this far, I want to recommend or say that the virus is still out there, and what we can do is to make sure that we stay safe, not just for us, but for other people, to understand that we're a community, so the actions that we do could have an effect on other people, and our job is to make sure that we can minimize the risk that other people have to face as less as possible. So, please try the simulation out, and I hope you enjoyed listening to my talk, and I hope everyone now can see how important it is to do certain things while dealing with the virus. And I guess washing hands isn't something really hard to do, but you thinking that it might be something that could potentially save someone's life would give you meaning to continue doing so, and making sure that you're sanitized, wearing masks, everything really, all those small things could be saving someone else. So please make sure to have that in mind and stay safe. Please enjoy the simulation. You can use it even if you don't have Wi-Fi, as long as you can access the file. So I hope you enjoy. Thank you for listening.